Oh, I wanted to stop beeping. Stop beeping. OK. All right. So let's see what people say. It's the limit as h goes to 0. Sometimes our variable is x, but in this problem it's h. And it's 1 over the square root of 1 plus the square root of 1 plus h. What is that limit? What did people say? OK, so 0 and 1 were pretty popular. 0.5 also popular. So there's 0, 1, and 0.5. Let's do a revote. And I'll let you pick between these three options, 0, 1, and 0.5. How would you do this limit? This limit, even though it's related to this whole stuff with like slopes and derivatives, is a perfectly good limit question for the midterm tomorrow. So it's a good one. Think about what is the first thing you would try to do this kind of limit. And we'll revote and we'll take it up again. So try to pick between one of those three options and really try to do it carefully. OK, here it is. It's up again. OK, there's like 15 seconds left. OK, let's take a look. On the second vote, people on 0, 1, 0.5 takes the lead slightly. 0.5 is the correct answer. If you said 0.5, this is good. You know how to do easy limits. If you said 0 or 1, then you should pay attention while we go over it. So this was the very last limit, secretly, in disguise. This was the very last thing we did on Wednesday's class. So if we go back to Wednesday's class, you remember we were on page 437, and we had this table. And this table was telling us all about the function, the different functions. We did the whole column for the function x squared, and then we started the column for square root of x. And we got this nice difference quotient, which is this difference quotient, 1 over square root of x plus square root of x plus h. And if you plug in x equals 1 into the difference quotient for square root of x, so this is the difference quotient, and you plug in x equals 1, you get 1 over the square root of 1 plus the square root of 1 plus h. That is where the warm-up problem came from. It's the difference quotient at x equals 1 for the function square root of x. And to do the limit as h goes to 0, that limit will give you the tangent line, or the slope of the tangent line, rather. Slope of tangent line. Slope of tangent line. OK, how do you do this limit? This limit is one where you can just plug in. Why do I know you can just plug in? Well, the base function is the square root function. The square root function is on our list of continuous functions. Continuous functions mean you can just plug in. So the square root function is there on the bottom. We're doing some combination of dividing, adding 1, but none of those operations are kind of bad. We're never dividing by 0 or anything like that. All the operations are allowed, so this is one where we can just plug in. Question here, yeah? Mm-hmm.
Since you did the table, those options that we put there, you know you plug in. If you just look at them.
I think basically the way I would say is you should always try to just plug in and see if something goes wrong. So things that can go wrong are like dividing by 0, that would be bad. If you have like an infinity or something, like that would be bad. If you plug in 1 and you get a good number, and the functions you plugged into, I think the other detail is that it's the square root function, which is on the good list, then it's always fine. So if the functions are on the good list and you plug in and there's nothing breaks, then it's all good. and the limit laws cover you, and they say, yeah, it's going to work out. So the only times it's going to be bad is when you plug in and you get a 0 over 0 or something like that. Then you have to do some more work. In this case, there's no extra work to be done. We just plug in and it works. Yeah, so we get 1 over square root of 1 plus square root of 1 plus 0. The square root of 1 plus 0 is also square root of 1. 1 over 1 plus 1 is a half. And that is why the answer was a half. And that's how I would do this limit. But it's a good lesson about plugging in. So you should always try to plug in first. If you have a fraction, you can plug in on just the top and just the bottom separately and see if you have a type 0 over 0. And then you can have all your training of what to do in the situation of a type 0 over 0. So things like knowing when it's type 0 over 0, that means we have to do some extra work. It's not that the answer does not exist. It's not that the answer is 0. Anything could happen. It could be any of these things. We have to do more work. Yeah, question? Was there another question?
You said that there's been fractions. Fraction has to be on the bottom, fraction has to be also on the top.
So I'm saying if it's a fraction, you can look at what happens at the top and the bottom separately. So you can sort of like plug in on them separately. And then if they both make sense as numbers, like if you get 3 and 7, then the answer is going to be 3/7, you're happy. But if one of them on the bottom especially is 0, then it means you got to keep your eyes peeled and like figure out what's going on. Yeah. Okay. Great. Any other questions or comments about this limit in particular? So like I said, the rest of the class, we're going to go over these questions that were submitted on CampusWire, but we probably won't have time for all of them. So I made a little vote where you can tell me what type of question you want to do first, and I'll pick that type of question from CampusWire. So that is this question here, what topic should we do? And there are exponential growth problems, logarithm problems, sequences, limits, that kind of thing. And you can tell me what you want to do. You can also not vote. That's fine with me. Pick any or all you want to do. I'll do them in order of what got the most votes to the least votes. So yeah, maybe I'll just wait till we get to like 30 votes, and then I will take it up. So I won't start a timer. Yeah, I mean, so there's limits and sequences here. I think limits is definitely a big concept because limits is in chapter 10 and in chapter 8. But sort of in terms of like the chapters, it's pretty well spread out. There is a bonus. Well, you'll see when you do it. Yeah. Okay. Okay. Let's look at what the votes are. Okay, 43 people voted. 26 here, 25, other one, 23 for sequences. So I guess very narrow vote. Let's start with these two. Let's start with this exponential growth problem. And this was a good one. And I think this one also has some good problem-solving strategies in it. So this is the problem, and it is the most upvoted, I think, on CampusWire as well. It's this problem, right? Can you do this question? In 1975, the population of Toronto was blah. In 1982, it was blah. Use an exponential growth model to find the population later. So great question. Let's start with this one, and then I'll do limits after. Okay, and I have a whole new page. A whole new page. Okay. So this population of Toronto problem, it's from the practice midterm, if you haven't seen it before. It was also taken directly from the homework. So here it is. Okay. And this is a good problem where you have to practice the skill of taking what you know, thinking of what you have, and like charting a map of how you're going to get from what you have to where you want to go. So what do we have? What are we given? What are we given? And how are we going to get to what we want? Which is what we want. And this is a good problem where there's in-between points, and it does a good job of making sure you're using the formulas that we've done in the class as intermediate points. So in this particular problem, the key thing, maybe I'll read the whole problem out loud once. In 1975, the population of Toronto was 2.77 million. In 1982, it was 3.133 million. Use an exponential growth model to estimate the population in 2021. And if you try to just like kind of do it all at once, it's too much. You got to break it down into smaller parts. And in this particular case, the key word, I think, is the exponential growth model. And that is pointing to a specific formula that we did in class. And if you don't know what this exponential growth model is, you will never be able to do this problem. So ideally, you have it on your formula sheet. If instead of having you guys write the formula sheet, I was going to give you a formula sheet, it would be written there. But if you bring in your own formula sheet and you don't have this model written down, then you're going to struggle with this. And that model is this model, A e to the kt, A e to the kt. So we're going to use this model. This model, you need to kind of like know the basics of it. There's two parameters, A and K. This model's a function of time. So A and K are the two parameters, and it's telling you as time progresses what the function is doing. What are the values of the function at different times? They depend on A and K, and T is what you plug in. T is like the X value. So you have to know this function. This is like the starting point, starting here. Like if you don't know that, I think you're really in trouble for this function, for this problem. If you have this function written down, you can write down what you are given in terms of the function. So when someone says the population of Toronto in 1975 was 2.770 million, you can write that down as f of 0, this is what you were given, is 277000. So I can convert this piece of information, this little sentence, into that nice line. And I already made some nice choices here. I made this t equals 0. So I chose t equals 0 means 1975. And this is when you do these types of problems, it's always nice to make one of them, one of the times in the problem, t equals 0. And there is a special reason for that. And that is because f of 0 is always equal to the parameter a. F of 0 equals a. So if you've done a few problems with these examples, you know that a is the value of the function at 0. And in this case, they told us the value at 1975. So why don't I make that times 0, save myself some work? And if you do this, look, we've already found the value of a. From the first piece of information, we found the value of a. What else are we trying to do? Well, what else are we given in the problem? We're given that in 1982, the population was 3.133 million, thousand. So we can write that down. And here we're gonna write that down as f of something equals 3133000. So f of something is that. You got to figure out what the something is. If you write 1982, you'll be wrong. It's not f of 1982. It's f of 7. And the reason it's 7 is because 1982 is 7 years later after t equals 0. So by the choice we made earlier, it's going to come into play here. So that's f of 7. That's what we're given in the problem. We've squeezed all the information out of the problem, right? We were given two pieces of information about populations, which was f of 0 and f of 7. And we want to get to what we want, which is the value at some later time. So what we want can be written as f of, you could write 2021 minus 1975, which is f of 46, I think. That's what we want to find in the problem. So we're given f of 0 and f of 7, and we need to find f of 46. I really think that we've actually already done almost all the work in this problem. Everything that I just did is 90% of the work in the problem. Unpackaging what you have, making use of this exponential growth model, setting it up like this. If you do all that, then you're in good shape to finish the problem. Any questions or comments about what we've done so far, or like where we're going? How you kind of decode the word problem part of it? Yeah. Yeah. Yes, that would work. So you could equally well, okay, this is like, let me put this in as a different thing. You could have done f of 1975 and f of 1982, and then this is 2770, and this one is 3133000, and you want to find f of 2021. This will work. It'll be an extra amount of work. And the reason is f of 0, it gives you the a value right away. So if you have done practice problems with this, you'll know that the a value is f of 0, and that if you have a 0 time in your problem, it helps you because it makes things easy. So you will eventually get the right answer, but it's more work and there's more room to make a mistake. So I highly recommend you do it this way that I have written. The other way should be exactly the same. In fact, the two functions should be the same function, just shifted by 1975. So of course you will get the right answer. Yeah, great question. Okay, so if you have this set up, the meta problem, and I think of this as like the halfway point between what we're given and what we want, are solving for these two parameters a and k, solve for a and k, right? And if you know that this is what we're actually trying to do, we're actually trying to solve for a and k. And if you can figure out what a and k are, then you can figure out f of 46 just by plugging in. And there's two unknowns, a and k, and there's two pieces of information, so they kind of like everything gels up in your brain. So if you know that this is the midpoint, solve for a and k, then the whole thing makes sense. We're going to take the two pieces of information we know, we're going to solve for a and k, and then we're going to use that to get the value of the function. It's like it's all kind of clear in your head. So having this like roadmap, what you're given, what you want, what's the midpoint, is like a really good skill to develop. I think this is like basically the reason they make you take math classes, so you do this kind of problem. Okay, so let's do it. We're going to solve for a and k, and because of the choice we made, one of them is already done. A is already done. We know what a is. A is 2,770,000. That's a. How are we going to solve for k? Well, we have one equation, which is f of 7 is 3,133,000, and we can use that to solve for k. And that's because f of 7 is equal to a times e to the k times 7. So we have an equation, a times e to the k times 7 equals 3.1 million. And we know the value of a, so we can even plug that in. Let me write it out in as many steps as I can to keep things clear. So this is this, and therefore 2,770,000 times e to the k times 7 equals 3,133,000. So that's an equation with an exponential. If we can solve it, we'll get the value of k, and then we'll use the value of k to answer the question. So this is where the whole question has become, can you solve this kind of like algebra thing, which was another topic we did in the course, right, in exponentials and logarithms. To do this one, you have to know how to rearrange and get rid of this nasty exponential. So the way I'm going to do it, I'm going to divide by 2,770. That's going to move that to the other side. So it's going to be 3,133,000 divided by 2,770,000. And I have these two things in a fraction. Why don't I cancel 1,000 from the top and the bottom so I don't need to write as many numbers? So why don't I do 3,133 divided by 2,770. Then there's less to write. It's the exact same fraction. So that's e to the 7 times k is equal to that. What is k? What is k? Let's build a, let me try to fit k in over here. Yeah, okay. To do k, if I have e to the power something equals something else, I can take the ln, the ln of both sides. So I can do the ln of both sides, the ln of this. And let me do the ln of that just to be safe. And then you get the ln of e to the k times 7 equals the ln of 3,133 divided by 2,770. And the thing about ln is it perfectly undoes e to the power. The ln of the exponential is just whatever was in the exponent. In this case, it's 7 times k. So by doing the ln of both sides, I effectively got rid of that exponential. Now it's perfectly set up to solve for k. I have 7 times k equals something. What is k? It's 1/7 of the thing. Ln of 3,133 divided by 2,770. So I've solved. Now I've solved for k. I've done the halfway point. I know the value of a is this, and I know the value of k is this. And by using those two together, I'm going to get f of 46 just by plugging in. So really, I've done all the hard work of solving for a and k, which again was nowhere in the problem. Nowhere in the problem does it say solve for a and k, but it's something you have to know how to do. Any questions or comments about where we've gotten to so far? In the last little bit is just plugging in. It won't be so hard, or I don't think it'll illustrate much, but we'll do it. But it's a good time for questions. Okay, let's try plugging in. So we want to do f of 46, and again, we calculated the 46 because we set our 0 point at 1975. What is f of 46? Let me write it out like this. F of 46, and it's going to be a e to the kt. A is 2,770. Let's write it out. A e to the k times t, and t is 46. In our case, a is 2,770,000, and k is 1/7 times all this stuff. If you have 1/7 times a bunch of stuff and you multiply it by 46, you have 46 sevenths. So 46 divided by 7 times the ln of 3133 divided by 2770. And that's the answer. That's a perfectly valid answer. On your midterm, if you write that in the box and it's correct, that'll be full marks. Like you don't need to do it on your calculator or anything. It is a reasonable idea for a problem like this to type it in your calculator and make sure you get a number that is like, I don't know, like 4 million or something would be reasonable. If you get 50 billion, then probably you made a mistake. If you get 12, like you also probably made a mistake. So it is like a reasonable idea to plug it into your calculator. I'm going to leave it just like this. Everybody's calculator is different, so you should practice plugging it in on the calculator you're going to use at the actual midterm. If you go watch the practice midterm solutions, you'll see the actual answer. Maybe I can write it out, and then people can compare. So what did I get when I did it? Practice midterm 2. I got 6.222 million. So 6, 2, 2, 2, like this, something like that. So it's a good skill to make sure you know how to do that correctly, you know where the ln button is, stuff like that. But again, it's perfectly fine to just leave it like that in the final answer. I would really only recommend doing decimals if you're stuck and like that's the only way you know how to do it, or to like sanity check and make sure the population of Toronto really is like roughly 6 million, that adds up. Okay. Yeah, question? Yes, I can scroll down. Yeah. Okay. Okay, any other questions or comments about this one? Yeah. Yes, you can just leave it like this, and that will be perfectly correct. So if you write that in, that'll be a perfectly fine answer. In this case, it's a number with like millions and millions, and so it's quite long. On the actual midterm, I tried to make the numbers like smallish so that they would fit in the boxes. So this one I took directly from Math1030, so that's why it's long, but they should roughly fit in the box on the actual midterm, and it's totally fine to leave it like that. This is a great answer. Yeah. Yeah. Yes, you can on your formula sheet you can put examples. That's totally valid. You could write this out if you want. Sure, that's great. Yeah. The only limitation is that it's one-page double-sided. So of course you don't have room for every possible example, but you have room for some that you find helpful. You can write them down and write them in your own words. Then it's great. Yeah, great question. Anyone else? Okay, and again, if you go to the Math1030 homework on exponential questions, there's a lot more like this. So if you're like, I feel like I wouldn't be able to fully do this problem if it was on the midterm tomorrow, then practice doing just those Math1030 questions that are about exponentials. The real question I took from either lecture or the Math1030 questions or some like combination of that style of question. Okay. Questions or comments about exponentials? Otherwise, I'm going to go on to limits, which was the next most popular thing. Okay, let's do some limits. So the limits I can offer you, there is a limit like this. This one involves one-sided limits, and it also involves the curly bracket with the piecewise functions. There's this limit. This limit is a classic like 0 over 0, which is also good to know. Those are two of the big kind of styles of limits we did. What other? I think those are the main limit questions. The other ones are about sequences and stuff. Okay, so great. So these are the two. Maybe I'll let you guys we'll do a hand vote. I think we probably have time to do both, but which one should we do first? Should we do question 11 or question 6? Those are the two options. Who thinks we should do question 11? A few people. Who thinks we should do question 6? A few more people. I think question 11 was slightly more popular. So we'll do that one first, and I think we'll have time to do question 6 as well. So question 11 is the limit, and I think I can copy it exactly. Copy. Okay, so question is the limit as x goes to 0 minus of the absolute value of x divided by x And it's giving you a hint. It's telling you the formula for absolute value of x. OK, that's very nice. I think this one, if you know what you're doing, you can put together the answer in like 1 minute. So if you've seen these problems and you know like how to deal with these piecewise functions, you can like do this one pretty quickly. So I'm going to give you guys 1 minute. Try to do it. If you're stuck, it's totally fine. I'm going to show you how to do it. But I think it's more instructive if you really try it and like think of what would you try? What would be the first thing you would try? What would you do? What answer do you get? So let me give you just like 1 or 2 minutes here. And I can come around and answer questions as well. Let's do a minute and a half. Try it and see if you can do it. And if not, I think it'll still be instructive for you to try it. OK. So a minute and a half. I'll come around if you have individual questions. OK. So who thinks they got it? Who thinks they got it? Who would need more time to try to get it? A couple people. Who thinks they're stuck, like they need help, need a hint? OK. So let's slowly do it. The first thing, I think there's 2 levels to this problem. And the first level is all about how do you handle these piecewise functions, right? And the piecewise functions, the fact that this thing is the absolute value function is completely irrelevant to this problem. You should be able to handle any piecewise function. So if the question just said, please find the limit as x goes to 0 minus of f of x divided by x, and f of x equals square root of x minus x if x is greater than 0, and this if x is less than 0, that's the exact same question. And like there's nothing special about the absolute value function. I'm just saying it's a black box. Like this f of x thing is a black box, and the only thing you know about it is it has these 2 branches. And if you know how to look at which branch where, then you will be able to perfectly solve the problem. So that's the first thing to decide is which branch do we look at now? Which branch now? Branch now. And if you know which branch, then it's going to simplify the problem into an easier problem, and then we're going to use our 0 over 0 problem skills. But this first thing is figuring out which branch we're talking about. And the key is in x goes to 0 minus. X goes to 0 minus. So you have to know what that silly minus sign means. X goes to 0 minus means a very specific thing. It means we're approaching 0, but on the number line, we're coming in from the left. So here is x equals 0. And x goes to 0 minus means we're coming in from the left side. We're coming in from the left side. And from the left side are values that are negative. They're a bit smaller than 0, negative numbers. X is less than 0 here. So you should know what this x goes to 0 minus means from pictures, like we did these pictures in class, like coming in from the left, going in on the graph. But also algebraically here, x is less than 0. And when x is less than 0, we are talking about this branch of the function. So this is the first thing to realize. Because it's x goes to 0 minus, only that second branch matters. That's the only thing that matters. Everything that happens up here, this is irrelevant to this particular problem because it's x goes to 0 minus. So what can we do? Wherever we see the function f, so f of x, we replace it with whatever is over here, with minus x. The function f of x is the same as minus x when x is less than 0. Those are the only x's we care about. So this is the first step in simplifying, is that this becomes the limit as x goes to 0 minus. Every time we see that silly guy, we replace it with minus x. So we have minus x divided by x. Maybe I'll keep drawing this guy in purple. That guy didn't get touched. So that's the first step. Knowing how to do the limit from the left and knowing that it only involves one branch. This is the same idea as graphically when you only look at to the left of the point. So that was graphically, this is algebraically. Are there any questions about this idea of, yeah? Yeah. And then it says here. Here, yeah. Let me make it a bit better. Yeah. Here. And so by here I mean everything to the left of x equals 0. That's what I mean by here. And that is exactly what this limit cares about, getting close to 0, but always on the left side. Yeah? Why? You mean, why is it that? What do you mean by the bottom? Yes? Yeah. Ah, okay, this is a great, okay, this is a good point. It's like, I just left the over x part, I just left that alone. I didn't touch that. And that's because x is always x, right? So the f part, the absolute value function, it's like multiple different characters. Like sometimes it's like this, sometimes it's like that. The stuff on the bottom is just always x. So you never need to replace it with anything, it's always x. So we just leave it alone. X is just always x. So the bottom, we haven't touched. That's right. Yeah, it's we have simplified. We said f of x gets simplified into minus x because we're only looking at this branch. But the function x is just always x. So there's like no simplification needed. It's just always x. Okay, hopefully that helps. But yeah, so the stuff on the bottom we just left alone. Okay, minus x divided by x. That's what we have. Okay, so now we've dealt with the part of the problem where we have to do these piecewise functions. Now we have the function minus x over x. And this function, when you have a limit like this, the first thing you should do is just like the problem we started with today, you should try to just plug in. Let's try to just plug in. Try to just plug in. And when you try to just plug in on this one, you'll notice that the top is the limit as x goes to 0 minus of x. We're plugging in x equals 0. You get minus 0, which is also 0. So the top on its own is 0. The bottom on its own is also 0, because x is 0. So if the top is 0 and the bottom is 0, this is exactly the type 0 over 0. Type 0 over 0. So I always put it in quotes. It's not equal to 0 over 0, but it is type 0 over 0. And we cannot just plug in. That's what it means. We have to do something else first. One of the things you can do is try to cancel out something from the top and the bottom. And in this particular case, they are actually extremely related because they're minus x and x. Minus x and x have a common factor, which is x. So you can cancel out an x. So simplify by canceling out an x. Okay? And when you do that, if you simplify an x from the top and an x from the bottom, then you get the limit as x goes to 0 minus of minus 1. So the only thing that sort of survives is that negative sign from the front. The x's cancel out, and you're just left with minus 1. And it seems a little silly in this case. It's exactly the same thing on the top and the bottom. But this is like a really good skill to know, is that when it's type 0 over 0, to look for ways to simplify. And when we do the next problem, problem 11 or problem 6, whatever it was, then you'll see that like a harder version of this kind of idea of simplifying from the top and the bottom. But in this case, it's sort of like simple, x on top, x on the bottom. And finally, we have the limit of minus 1. This one is perfectly fine. This one is a just plug in. It's exactly what you think. The limit is minus 1. So the limit of minus 1 is minus 1. It's always minus 1. Of course, it's going to be minus 1. So there you go. The limit is minus 1. That's the answer to this question. The limit is equal to minus 1. And once you do the limit, you'll know that it's none of these, right? None of these was the answer. OK, let me zoom out a bit for people still copying. And I can scroll down. Any questions or comments about that one? I tried to break it down into useful parts that have like transferable skills. OK, let's do the other one with the square roots. because that's also a good one. That's this one. Okay. Here it is. The limit as x goes to 4 of x minus 4 divided by square root of x minus 2. And as always, the first thing you could try to do is plug in. Because these are nice functions, like x minus 4 and square root of x minus 2. They are continuous functions. So if it works out to just plug in, then we'll be OK. We'll be saved by the limit laws that tell you it's OK to plug in as long as nothing bad happens. So if you try to plug in, then the top will be x minus 4, which is 4 minus 4, because x is 4, which is 0. And the bottom is the square root of 4 minus 2, which is also 2 minus 2, which is also 0. So unfortunately, this one is also a type 0 over 0, and it means we have to look for ways to cancel, to factor things out, make the top and the bottom have a common factor that we can cancel out, just like we did with x over x before. If we can do that again, we'll be happy. So how do we make a common factor appear? This is the question. How to make a common factor appear. How to make factor appear. OK, and this is something that came up last class. When you have these square roots, you should think of multiplying by the conjugate. That's exactly going to solve this answer. And I think if you don't remember that you're supposed to multiply by the conjugate, I think you're kind of stuck on these kinds of problems. So once again, if you have these square roots, you got to remember the trick, which is how do you make the factor appear? You multiply by the conjugate. And so in this case, it's going to be x minus 4 divided by square root of x minus 2. That's the original problem. And I'm multiplying by the conjugate, which is square root of x plus 2. So that minus becomes a plus. And to make sure the limit is all legit, I haven't changed the actual answer. I'm doing it on the top and the bottom. And now I recognize a difference of squares on the bottom here. So that becomes the square root of x squared is just x, and the square root of 2 squared is 4, and it's a difference of squares. So x minus 4 on the bottom. On the top, we have this product, x minus 4 times square root of x plus 2. That is just whatever was on top before. And now we have the limit as x goes to 4 of this stuff. OK, and now we're perfectly in a situation where the top is nicely factored. It has 2 factors, x minus 4 and square root of x plus 2. And the bottom contains one of those factors. It contains x minus 4. And so because the bottom and the top have a common factor of x minus 4, we can cancel out that factor. And hopefully, it won't be type 0 over 0 anymore. So this is a common factor of x minus 4. And once again, the trick of multiplying by the conjugate was to force this common factor to come out. In other problems, maybe there's another way the common factor comes out. OK, common factor of x minus 4 cancels from the top and the bottom, and you are left with the limit as x goes to 4 of square root of x plus 2. That's the only thing left over. And now we're in a situation where just plugging in does work. So just plug in, and it will work. Just plug in. The square root function is continuous. You get square root of 4 plus 2. 2 plus 2, which is 4. So that's the answer to this one. The limit is 4, and those were the steps and the explanation. Any questions or comments about this? OK, so again, this one is quite tricky because you have to remember this multiply by the conjugate trick. If you don't remember the multiply by the conjugate trick, then you will be stuck at this point to how to simplify. In other problems, there are other ways of simplifying. OK. OK, so it's 5:10. I think we have time for one more. I'll put up that poll again. You can vote for what you want to see next. If you want to leave now, please also just leave during the poll. There's no reason to stay unless you want to see another one. So I will do a copy of this poll one more time, and then I'll go for the most common one. It might be sequences. We'll see. One second. OK, so this is open again. Vote for what you want to see next in the last 10 minutes, or just leave if you want to leave. It's up to you. I meant like in an alternate universe. Yes, I meant, so you guys, what I said is you guys No, I don't want to make them first, because I want people who study hard and have good sheets to do better. It's a trick to make you study. No, it's like if you come to the exam and you haven't done your sheet, then you get nothing. Yeah. On the other hand, I think it's like if you study hard and it's easy to make a good sheet.
Yeah, actually, stuff is not well.
Okay.
Just simple stuff. So I don't know. Like,
Okay, so 33 people voted. Let's see what you guys want to see next. Okay. Logarithm algebra. Okay, so we did one of these already, right, in solving for k. Let's do another one. And there was some on here. The ones on here were these kind of ones. Let's do this one. Okay. So here are some problems. Let's start with option A here. And option A is particularly easy because somebody already made things have the same base. So if they have the same base, then everything is a breeze, because if they have the same base, then the exponents must be equal. So you can go straight from this. You can go to therefore. You could skip all the way to 1 minus x equals 4. Right? If 10 to the something equals 10 to the something, the two somethings have to be equal. So you could skip all the way to 1 minus x equals 4, and then you can solve it. It's not so bad. But let's pretend they weren't the same base. How could you then work on it? And the answer always can be, if you take the log of both sides, then the equation will still be true, and then you can use log rules to simplify. So here's one thing you could do. You could do the log of 10 to the power 1 minus x, and then you could do the log of 10 to the power 4. And actually, the log base anything will work. So why don't I do the log? Let me do the log. This is like a crazy thing to do, but let's do the log base 7. Let's do the log base 7, just to show that no matter what base you use, if you know the rules for how to simplify, it's going to work out. And the most important rule with the logs is this exponent rule, that the thing in the exponent jumps down. So if you have log of something 10 to the power 4, then that's going to be 4 times the log of everything else. Okay. And then over here, you're going to have 1 minus x, and then you're going to have the log of 10. Okay, and here is one other place you can make a mistake, is if you forget brackets around the 1 minus x. So don't do that. Okay. Okay. So 1 minus x times the log base 7 of 10 equals 4 times the log base 7 of 10. Because they started with the same exact base, 10, these two things perfectly cancel, right? This log base 7 of 10 and this log base 7 of 10, they're both on the left and the right-hand side. They perfectly cancel out, and you get the equation 1 minus x equals 4, and now you can solve for x. So hopefully you can solve 1 minus x equals 4. To show you how this works, let's make the question harder. Let's pretend the question said e to the power 1 minus x equals 10 to the 4. Let's pretend that it said that. This is a new question, And how would you solve this question? Well, again, now they're unequal bases, so you can't do a shortcut and skip, but the strategy of apply log and then have the exponents hop down, that will still work. So I'm going to apply log. Any log will work. You will get to the right answer. In this case, I think it's a little easier to apply ln. So I'm going to do ln of both sides. So I have the ln of e to the 1 minus x and the ln of 10 to the 4. The ln of 10 to the 4, again, by simplifying, becomes 4 times the ln of 10. Right? The 4 jumps down just like before. The ln of e to the 1 minus x, again, you can do it in 2 steps and bring down that 1 minus x. Or you can just know the fact that ln and exponentials undo each other. So the ln of e to the 1 minus x is just 1 minus x again. And you have 4 ln 10. If you want to do it in 2 steps, you would bring that 1 minus x. That would hop down by the same power rule as before. So 1 minus x, and then you'd have the ln of e. And you might know that the ln of e is exactly 1. The ln of e is what power of e to get e? It's the power 1. So in any case, you get 1 minus x equals 4 ln 10, and then you can solve by moving to the right side. 1 minus 4 ln 10 equals x. Okay. So that's an example of one. Let's do one more maybe in the last couple minutes if you guys want. We can do this one. This one will involve, it'll turn into a question about quadratic equations because in the exponent there, the x's we're solving for involve quadratic equations. So 3 to the x squared minus 3x equals 81. I'm going to turn it into something by doing the log of both sides. Let me do the log of both sides. And let's do the ln. Let's always do the ln. Why not? The ln of 3 to the x squared minus 3x equals the ln of 81. And now I simplify. The stuff in the exponent jumps out. X squared minus 3x times the ln of 3 equals the ln of 81. And now I can get x squared minus 3x on its own by moving the ln of 81 divided by the ln of 3 over here. Okay, and ln of 81 and ln of 3 individually are both really weird numbers, but if you type this in on your calculator, ln of 81 divided by ln of 3, your calculator should give the nice number, which is that this is 4. This is 4. Okay, and why is it 4? It's 4 because 81 is 3 to the power 4. So it's not a coincidence that it's 4. And now you have x squared minus 3x equals 4. This is like one of the last core skills that we did is solving quadratic equations, knowing how to factor them, things like that. So x squared minus 3x equals 4 is the equation x squared minus 3x minus 4 equals 0. And this equation you can solve because you can factor it as x minus 3 times x plus 1. And when I say x minus 3, I mean x minus 4. Okay. So x minus 4 times x plus 1 equals 0, and therefore x equals 4 or x equals negative 1. Okay, but those are, again, some of the core skills you'll have to know. Okay, I'll be around for a few minutes if you have more questions. Feel free to come ask. Otherwise, see you guys tomorrow, and good luck.